Reggeization.
Okay, so let's proceed with our last talk for today, and Jan will tell us about Reggeization from Renormalization.
So thank you again to the organizers for organizing this great workshop. I'll be much briefer today than last week. So I want to talk about some recent work we've been doing on trying to better understand Regge theory, in particular in QCD or non-planar theories, using some modern techniques of effective field theory and the renormalization group. And so this is work in collaboration with Anja Ga, who's a student, and then Ian Stewart, and based on also work of Ira Rothstein. So last week, Volodya gave this very nice talk on integrability in n=4, where he showed this exact result for the leading twist 2 Regge trajectory in the theory. So in this J and delta minus d over 2 plane, he gave this very nice finite coupling result for this trajectory. And in particular, he was able to kind of analytically continue it to the entire regime, and he could read off, for example, the 3-loop BFK eigenvalue around j=1. And so what we'd like to do is to try and kind of understand how much of this is known when we depart from this very well understood example. And so if one looks at this Regge trajectory, so this region up here, this region above j=2, this is kind of very well understood, both conceptually and just from a practical point of view, if we go to, for example, non-planar theories or QCD. So in particular, you can do calculations to, for example, for-loop order and understand things at a very, very quantitative level. And so I discussed last week how kind of the perturbative data in this region allows you to make predictions, for example, of these energy fluxes at collider experiments. So I showed results for these, for example, energy correlator observables. And so these use all kind of the anomalous dimensions at finite spin greater than 2, and also in the j to infinity limit. And so this is kind of very well understood, even if we go away from the planar limit where we have integrability and stuff. So where things get a lot murkier is as we go down to this region near j=1, so what is sometimes called this BFKL region. So for them, they could do it amazingly, but this is where things are kind of very murky if you go, for example, to QCD. So this physically, what this region describes is forward scattering. So it describes, for example, 2-to-2 forward scattering, where you exchange a bunch of stuff, and I'll go through this in a bit more detail in a moment. So this physically describes this forward scattering region.
In the plot, does it refer to dimension of single trace operator?
Yeah, so this is just, the leading twist 2 trajectory, yeah.
Not the double.
So there's more, and I've completely ignored them for now. So, yeah. And so there'll be it's even less well understood if you go over there, which I'll say in a second. And so this region is conceptually and technically extremely poorly understood in QCD. So just at a, for example, technical level, one can only do like 2-loop calculations, and so these are done in the 90s. And so even though we have much more powerful techniques coming from scattering amplitudes, because it's kind of conceptually not very well understood, one has not been able to promote these to the level that kind of everything else has been moved to. And at the kind of conceptual level, there's all these kind of Reggeon effective field theories, or these kind of Lipitov spin chains. And the kind of status of these is a little murky, and they're hard to use for explicit calculations. You also have some conceptual issues that you seem to have some very large number of trajectories that are all separated by kind of 1/n, and these kind of pile up in some way and it's just not understood at all what goes on in this picture. And so what we'd like to try and do is to...
1 over n is 1 over nc? Or?
Yeah, 1 over nc. So there's a kind of infinite set of trajectories corresponding to the exchanges of these, which I'll come to in a second. And they all kind of pile up there with some very small separation. And then these all kind of, something drastic has to happen before they run into this. And so what we'd like to try and understand is some way of computing things kind of systematically around this j equals 1 or forward scattering limit that applies also in QCD or just non-planar, let's say n equals 4. And so the way, so first just to review a little bit, because this Regge theory is kind of something very old that people may not be super familiar with. So first a little bit about what is known in generic. So this is in QCD or generic gauge theories. So what one is trying to describe, as I said there, is this Regge or forward scattering limit. And so you can do multi-Regge, but here I'll just restrict to 2 to 2. Where the Mandelstam variables exhibit this particular hierarchy. And so the way that people have tried to organize this is in terms of effective states propagating in the T-channel. So you have some kind of effective states which propagate in this T-channel. And so because these, if you're restricting yourself to some exclusive scattering process, you don't kind of radiate additional color. And so you typically organize these by the color representation of the object propagating in the T-channel. Just because that's conserved, if you kind of think about these as moving up, which will ultimately be what comes from the renormalization group, you just have some kind of fixed color state in this. And so the most famous is the octet channel, which you can think of as kind of the dressing of a single gluon. So it's in the H channel, so that you can draw it as some fancy gluon, like this. And in this, what happens is that the single gluon exchange, which would give a kind of S over T singularity like this, it so-called Reggeizes, which is essentially just it develops some anomalous dimension. And so it goes instead like this, with an object here, which is called the Regge, or this is like the Regge exponent or Regge trajectory in the theory. And so this in QCD is known to 2 loops, and as I'll show later, there's some kind of arguments about how to define it at 3 loops from conceptual issues, which we'll come back to in a second. So the next thing which is known is what is referred to as the Pomeron, in particular the hard Pomeron. And so this is the singlet representation. And so you can think of this loosely as a kind of bound state of 2 of these octet regions. So you have kind of 2 of these objects propagating the T-channel, and they can kind of interact between each other, and they're in the singlet representation. And so this is described by what is referred to as or their kind of evolution is described by what is referred to as this BFKL Hamiltonian. And the way you can think about this, and I'll come back to it later, is that these objects have some kind of transverse momentum, and they can exchange that transverse momentum. And so it's some evolution equation which kind of mixes these. And you can solve it and find the kind of eigenvalues of this, which are what was predicted and shown in this plot last week. And so this object is known at 2 loops in QCD from the work of Fadin and collaborators in the 90s. And so then what happens is kind of beyond this, which is relatively limited from the modern perturbative perspective, things become very murky at 3 loops and beyond.
Already, at this level, one sees that the perturbative expansion is going to break down.
Or, so you mean in terms of this converging very poorly, or?
Just violating the Poisson.
Oh, yeah, good. So there's many, if you restrict yourself to this, there are problems. Yes, exactly, yes.
There are clearly problems, but it's an indication that higher order corrections are going to be even bigger.
Yes.
So,
Yeah.
this is at best some kind of a double-scaled asymptotic series.
Yes, so there's a number of problems, and so again, it depends what one's exact motivation is. And so from a modern person, so there's obviously actually applying this to, let's say, like physical forward scattering of hadrons. That's not something I'm personally optimistic about. But one reason why these are very nice is, for example, for the modern amplitude bootstrap program, they allow you to predict perturbative expansions to very high orders. And so often these programs use information from Regge limits or other limits as inputs. And so this is just even within the perturbative series trying to predict high orders in the perturbative series and understand the organization. But for actual scattering, it is.
In the bootstrap, you don't input
The perturbative amplitudes bootstrap. So
perturbative.
yeah. So this is really just in perturbation theory, and also so when I'm talking here about BFKL, there's kind of an amplitude level BFKL, and there's a real like cross section level BFKL, and all be restricted. They're related by kind of a cut essentially, but all be restricted to really just an amplitude level. And so then there's still problems about what it's predicting, but it's really just predicting partial structure of some higher loop amplitudes. Yeah. And so at 3 loops, things become very murky. And so one of the reasons is you get into a regime where, and so these are kind of standard lore, where you kind of don't know what happens, but if you try and use these, for example, Reggeon field theories, you can have strange things like Reggeons splitting into multiple Reggeons, and then you kind of don't know how to talk about, for example, what it even means for these Regge trajectories, or kind of how to actually compute these from a first principles setup. So if you don't have a proper field theory, it becomes very confusing what you're trying to do. And there's even kind of weirder things with Pomeron loops and stuff. And so what one wants to do is to have some kind of systematic effective field theory and renormalization group techniques to understand this. So you want some kind of way where you can really do this with some kind of well-prescribed rules and just compute what goes on. And in particular, one wants kind of operator definitions of these things or of these like spin chain pictures so that one can extend them in non-trivial ways. And so the way that we'll do this is using this effective field theory plus the renormalization group. And so as I'll get back later to the actual interpretation of this effective field theory as compared to these like Reggeon effective field theories and stuff. And so we'll have a very different interpretation. But for now, I'll just explain why this effective field theory is a little bit different than the kind of standard way that you think about effective field theories. And so what we want to do is to develop an effective field theory that describes forward scattering. So you can have some loops with stuff exchanged in the limit where this t is much, much less than s. So this ratio of those two will be the expansion parameter. And so the reason why this is different than a standard effective field theory, so the way you normally think about some effective field theory is you have some kind of very high energy scattering, and you want to integrate out some high energy degrees of freedom. So the thing that's unusual about this is that by definition, there's no hard scattering. Otherwise, you wouldn't be in this Regge regime. And so there's no degrees of freedom which are really kind of integrated out in this standard sense.
Sorry, how does T compare to lambda QCD?
So here, because T, like this relates to your problem, so T has to be much bigger than lambda QCD. But here, because it's really, that would be like for applications to real scattering, and that's where you get into all the problems. But if you're just doing it in amplitudes, you can take this, for example, in like n equals 4 or something. This is really just an amplitude level. And so the thing that's non-trivial, because there's no high scale, everything in this process is occurring at a kind of virtuality of this t. So there's no large momentum transfer, and everything is occurring at the same virtuality. But where there's a difference in so normally for an effective field theory, you want some hierarchy of scales. And so unlike when it's a hierarchy of scales in virtuality, here you have a hierarchy of scales in the rapidity or the kind of light cone momentum of these degrees of freedom. So because you have a very small scattering, you have these two things going essentially undeflected along the light cone, and then some stuff exchanged between them. So if you draw their kind of you can plot their kind of light cone momentum. So these things all have a kind of p squared, which is approximately t. But you have some collinear degrees of freedom, which are at a very high. So you have, for example, these collinear degrees of freedom, which are at either a very high p minus or p plus along the two light cone directions. So these correspond to these objects here. And then you have some of these, if I draw them in orange, these kind of degrees of freedom which are exchanged. And so these sit at a scale of kind of t. And so these are what are sometimes referred to as soft degrees of freedom, which are kind of passed between them. And so these all live at the same virtuality, but they have a very different rapidity. And so this is why one can hope to have an effective field theory description which separates them. And so in particular, what one wants to do is to describe or derive some effective field theory which is based on a renormalization group flow in rapidity. So we'll kind of divide degrees of freedom in rapidity and then have some evolution which flows you kind of between these degrees of freedom. And so physically in this picture, you can think of this as these kind of flows like this in the t-channel as you go from one side to the other. And so this is how it will kind of map to these kind of pictures, for example, of these BFKL Hamiltonians. And so I won't go into too much detail about some of the technical aspects just because I don't have time, but I just want to kind of say that there's an analog of dimensional regularization which allows you to kind of regulate certain singularities in these rapidities and allows you to derive an RG. And this is known as the rapidity renormalization group. So this effective field theory will be formulated in terms of Wilson lines. And when you do perturbative calculations, you'll get divergences as these come right next to the light cone. And so these can be renormalized, or first of all, they can be regulated by inserting, so if this is my light cone direction, this is some momentum, I can kind of regulate them just like dim-reg, but essentially for boosts. So any boost invariant regulator will, of course, not separate these because these all live on the same hyperbola. And so you have to have something that breaks boosts. And so you can kind of, into your Wilson lines, you can insert certain factors like this. And then you put a parameter which is called nu, which is like mu in dim-reg, but it's essentially restoring the kind of boost dimensions. And so then when you do a perturbative calculation, you really just read off the poles in 1 over eta, and then you can derive what are called rapidity renormalization group equations, which take the form of nu d by d nu for some particular operator like this. And so this is nice in perturbation theory because it behaves very much like dimensional regularization.
What is this? N bar is
a light cone direction. So if I have, for example, this moving along the n direction and this n bar, so I can, for example, take these as just some basis of light cone directions. And then m bar is like one.
And what here breaks boosts? So this.
By explicitly putting this in, yeah.
So the trick is to have this meromorphic mode.
Good. So this actually, one of the problems here is that for regulating, that this is not analytic. And this is needed for certain technical reasons in the effective field theory relating to the behavior under crossing symmetry. And so this makes things a little bit more annoying. Sorry?
How do you extract it from there?
So you can still, it behaves, yeah, so this is the fact that this has this absolute value is only important in certain pieces of the theory. But for certain loops, this doesn't, like, so in a regime where these are all positive, this doesn't matter. And so it has a very specific role of regulating some of these off-shell instantaneous exchanges in this sector. But for standard loop diagrams, for example, up here, it behaves in a normal way, and you can really extract the poles and renormalize. And so this has been tested relatively well, and so in certain cases you can really prove that this is a good regulator. That's a, yeah. And it would be, so in certain cases where you have fully time-like kinematics, it's been understood how to modify this into an actual analytic regulator, which then behaves much nicer. And so this is one kind of unsatisfying aspect of this effective field theory that one would like to improve, but it's not understood how to do it in a way that regulates all the diagrams in the effective theory. But that's a very, yeah, that's something that one would like to improve. Okay, so I definitely cannot do this effective field theory justice, but I'll just kind of claim that, so there is an effective field theory, and you can really write down a Lagrangian, and again I'll be extremely schematic. So what one wants is some Lagrangian which describes the kind of dynamics along one light cone direction, then factorizes it from some dynamics which is going on at this kind of central rapidity, and then you have the dynamics along the other light cone direction. And so you can write down the Lagrangian, down here, which implements this at the operator level. So again, this will be very schematic. So you have some operator which is formed from specific Wilson lines, which describes the collinear dynamics here. You then have some kind of inverse of these like this. And so I won't go into the exact details of these operators, but they're made out of kind of essentially Wilson lines. And so if you perturbatively expand this, so these are each gauge invariant operators, but if you expand this to kind of lowest order, what you find is this will reproduce this Lipitov vertex describing kind of gluon emissions in this central region.
Sorry, but could you explain, so in EFT there's usually something is UV, something is IR?
Yeah, so now so this is one of the things that's confusing. So in this Lagrangian, for example, there's no matching coefficient on this Lagrangian. So it's uniquely fixed. So you have to do a bunch of matching coefficients, and these operators are quite complicated in terms of Wilson lines, but once you have it once, it's exact. And so what you now study are
What did we integrate out to get this?
You didn't really integrate out anything. You've reorganized things in this expansion of T over S. And so this is why it's confusing compared to standard effective field theories. And so you're not integrating out anything because everything's at the same virtuality. You've reorganized essentially QCD in an expansion in T over S, and now you have these flows in rapidity. And so you can, each of these, what you should think of is how you divide degrees of freedom between these. And so just like it's kind of standard renormalization
When I
group,
move orange line, it's like I'm dividing.
it's like, if I choose another color, it's like we're putting some like cut in the amplitude, like where kind of you move these up and down. What you incorporate into collinear or soft is described by these rapidity RGs. So there's like rapidity in different sectors, but there's no flow in there's no flow in mu. And so there's no real UV. There's like a high rapidity, which is like collinear. And so when you do calculations, just like a normal, when you calculate an anomalous dimension, you see like it comes from the UV of the diagram. So when you, for example, calculate loop corrections to this soft one, you see that it has divergences when it goes into the rapidity of this sector. And so that's how you're really extracting the kind of, you're kind of separating in rapidity. And so it's a very different style of RG. But at a technical level, so if one buys this, and there's like concrete operators that are written down, one thing which is very nice is it makes, for example, computing things like this Reggeization, which were previously done with diagrammatic arguments, extremely simple. So for example, if you want to compute, so the first thing one can do is reproduce old results. So if you want to reproduce this region or reggeization, you take just a single one of these operators and do the one loop renormalization. So that you can do this either as one thing that's nice about this effective field theory is you can compute things either from the collinear sides or from this soft side. So essentially you can either renormalize this operator or this operator, and they have to exactly match by consistency because it's just how you split things. And so to derive the reggeization, it's a very simple one loop calculation. So you can either just compute a diagram that looks like this, or you can compute a diagram on the collinear side that looks like this. And in both cases, you really just read off the 1 over eta pole, and you derive some RG, which is just tells you how this either soft operator, so there's just some standard anomalous dimension like this, or for the collinear anomalous dimensions, it's just half of that. And so now these are trivial evolution equations to solve. So if you just RG evolve these from the scale of root t up to root s, the solution of this just gives that the amplitude behaves like this s over t to the gamma. And so you just derive very easily the reggeization from this operator level renormalization. So you don't have to think.
Calculate gamma?
Yeah, exactly. So
Which is what?
So at one loop, it's like it's just proportional to the cusp. So it's like 4 Ca over epsilon. So these so it's the cusp anomalous dimension. So because one is working here at amplitude level, it's IR divergent in dim-reg. So this is where it'll be cured, for example, for the Pomeron, you can do it at the level of the actual amplitude squared, then it gives a physical or a non-IR divergent result.
It's positive.
I think it's positive, yeah. But it's also, once you take a little bit, it's an IR regular, or yeah, the Pomeron has the standard, yeah. So there what you compute is an evolution equation, and what you get is it's, instead is eigenvalue, and that is positive, so it's above j equals 1, which is the problem you're referring to.
Right.
Yeah.
This effective theory contains information about all color channels.
Yes, so yeah, good. So again, how much time do I?
I don't know, 10 minutes.
Okay, perfect, yeah. So what you get here, this is from the insertion of a single one of these operators. So if we do, I'll do the Pomeron and then I'll just say the generic thing. So you can also do, for example, the Pomeron. And the way you do this is you have to renormalize some time order product of 2 of these Lagrangian insertions. So it's essentially taking 2 of these operators and putting them side by side. And so pictorially, these are some pictures like this, where you can have, for example, some, I switched my color scheme, but some gluons going in between. Or you can also derive this, so this is the kind of soft side. Or one thing which is non-trivial, which you can do, which is actually computationally much easier, is there's kind of a collinear version of the Pomeron, which comes from certain loop diagrams like this, and a kind of non-planar version like this. And it's the combination of these two which give the Pomeron. So if you just renormalize this in the standard way, what you get is the BFKL Hamiltonian. But as you say, or as was asked, because these operators have a free color index for each of these, it derives automatically all the different color channels for this object. And so this will become important in a second. So this just shows that you can reproduce kind of standard things. But the nice thing what one can then do is just consider generic insertions of many, many, many of these objects.
Sorry, so far you're using some RG because you say you can independently compute soft and collinear.
Yeah, yeah.
And RG is the statement that dependence on eta will cancel when
Exactly,
you add
exactly.
the two.
Exactly.
But
Yes.
you're not really doing any running at this. Okay, well, RG say that this thing will exponentiate.
Exactly. So you compute. So this one has you compute the, for example, the central piece and its natural scale is at like this new is approximately root t, and then this object up here has nu at approximately root s. And so you compute the enormous dimension, and you just RG evolve up to this, which is capturing the logs in the between the two. But you can equally well evolve down. That's just saying you better get the same answer regardless of how you split it.
Or you can do the collinear computation.
Yeah, or you can do the collinear, and then you move those collinear ones down to the central region. And so this is very nice as a cross-check. In particular, often these collinear calculations, because you're in one light cone direction, are much technically simpler. And then in those sectors, the regulator behaves much nicer, and so these actually allow us to like kind of go to higher orders in an easier way. So the nice thing about this is one can derive kind of a generic organization. For arbitrary numbers of these operator exchanges. So again, this will be very schematic, but one can take like this. And so each of these will, for example, inject. So it will depend on the momenta which is injected. And they will also have some color label like A1, A2, etc., etc., etc. And so one can derive a generic expression for this amplitude, which will be some very complicated object in color space, which depends on all the momentum convolved in some way. And this has indices in both spaces, and then a similar J. And so then one can derive the renormalization group evolution equations for these generic objects. And so if one does this in the planar case, these just reproduce these well-known like BFKL spin chains of Korchemsky and friends, or Lipatov, Korchemsky, and Fadeev. But the nice thing is that here one can really do it with generic color indices and understand exactly what happens. And so the main two complexities which happen when you go for generic things is the first, you get number changing interactions. So these happen, for example, from diagrams that look where you can have kind of, for example, 3 of these regions transition into 2. And then the second problem, which happens when you have multiple color channels, is the quantum numbers. So if you're organizing them based on the color that can propagate, this rapidly gets extremely complicated. So for example, even if you have the state with 3 Glauber, or 3 of these operators interacting, what you need to study for this is objects which are in the 8 tensor 8 tensor 8. So this is already quite a big color space. And so in particular, the ones that are well known for this, so you get 2 copies of the singlet, which are just the Autoron and the Pomeron. But beyond that, you get, for example, 8 copies of the, plus a whole bunch of other stuff we won't worry about, of the octet. And so you have kind of a bunch of like friends of the region, which are all moving in there. And so if you just perform some overall amplitude calculation, you can kind of disentangle how each of these different octets evolve. And so what really happens is you have some matrix within this color space that can kind of mix and evolve, and you have to separately disentangle the kind of different eigenvalues, which are now spaced by 1/n generically beyond the planar limit. And so I won't go through the kind of technical details, but what we've done so far is to do this completely. So we've done this for 3 Glauber exchange. So we've done for like the kind of generic case for 3 operator exchanges. And so this kind of resolves 2 kind of issues which were appearing in the literature. So you can derive the full Hamiltonian, and you get a full, so you get some Hamiltonian which describes this evolution, which you can iterate and predict higher orders, some of which you can check. And so this kind of achieves 2 technical things. So the first is that if one looks at, I won't color this time, this object here, this actually reproduces at a kind of mathematical level what is often referred to as this 3-region vertex. So it reproduces what was kind of conjectured in the literature for this 3-region vertex. I'm going to put these in a different color. Although for us the interpretation is very different because it's kind of the scattering of 3 of these operators into 2 of these operators as one evolves in rapidity instead of some kind of decay of these operators. So the second thing is that we're able to disentangle all these color channels. And so we have kind of a spectrum of different anomalous dimensions, which are separated by 1/n. And so the third thing is that for us, what is very nice is that this individual operator, so with 1 operator inserted in the middle, so this single operator, or single operator exchange, renormalizes multiplicatively to all orders, so it never kind of mixes with other higher states. The only thing that happens is that these operators kind of scatter into each other. And so this is kind of, from the Reggeization effective field theory, which I'll discuss in a second, this is kind of a stable state, as compared to kind of these, which can quote-unquote decay. And so what one has is kind of these objects, which are to all orders in perturbation theory, is some gamma Regge, which is now really identified with the Regge trajectory. It's always diagonal, and so it gives some kind of all-loop definition of this Regge trajectory, which is really describing, so it kind of makes unambiguous what you actually want to refer to as the Regge trajectory, and will hopefully enable it to be computed at higher orders.
It's a singlet.
Or this one is the octet. Yeah. Yeah. Which is, again, not physical. But for if one wants to predict things in that channel of a scattering amplitude, one can do it. So I'll just very briefly go over kind of what is the, so one thing which one can ask is what is the kind of physical interpretation of this renormalization, or of this effective field theory, as compared to previous approaches. So this is quite different from, for example, the Reggeization effective field theory, in that it's really a 4-dimensional field theory which obeys, for example, like standard unitarity and cutting rules diagram by diagram. And so the way that one should think about this is you have the full QCD, you reorganize it as an expansion in this Regge effective field theory, or let's call this effective field theory, which is an expansion in T over S. And then the renormalization group equations, you get an infinite set of coupled renormalization group equations from the mixing of all these operators, and it is these that actually reproduce. So the rapidity renormalization group is what reproduces the kind of Reggeization effective field theory. And so in particular, it's just the evolution in the rapidity, which one can take as the Hamiltonian, and you can view these as kind of scattering of these Reggeization operators as you evolve in, or as you evolve. But the nice thing as compared to other approaches is we can kind of systematically derive the rules of this Reggeization effective field theory from perturbation theory and kind of build it up. And the other technical, as I mentioned, simplification is that this object seems to really be a kind of eigenstate. This kind of single operator is like an eigenstate of this Hamiltonian. And then when you go to higher orders, you have scattering of it, for example, like 2 to n scattering, but you don't have these decays. And so it kind of resolves some problems in how to think about this effective field, or Reggeization effective field theory.
So at which point you drop dimensions, because Reggeization EFC was some lower dimensions.
Yeah, good. So these rapidity renormalization group equations, because what they're describing is the passing of these, so when you do it's in the renormalization, that the renormalization depends only on the transverse variables of the chain. So in this picture, what's being passed between them only has this two-dimensional transverse momentum. And so this is what is like the spin in the Lipitov picture. So when you're passing between these or interacting up here, it's only talking between these transverse momentum. And that's because that's the degree of freedom, or that's the scale that's shared between like the collinear, the two collinears, and this. The only thing that can interact is at this transverse scale. And so it's in going to the rapidity renormalization group, which is where you drop the dimension, is that the renormalization group itself depends on less variables than the full field theory. But it's still a kind of complicated object because you have these kind of, once you allow number changing interactions, you really have kind of a field theory in the evolution in this eta variable. And so this is something which we've been just trying to understand. And so the kind of future directions we'd like to is understand if one can really use this to compute higher order BFL, and for example, better understand the generic structure of these Regge trajectories, or relation to these Regge trajectories and kind of light ray operators, and this, or understanding what exactly is this kind of Reggeization field theory, and if there's ways of, for example, exactly solving some of these scattering of these Reggeization operators. And that's it. Thank you.
Come back to the Froissart bound.
Yeah.
Do you see any way of being consistent with unitary?
Yeah, so this is one of the so one of the reasons why this is very hard. You can one can understand. So typically, what these in all these approaches, they're trying to resum to some particular logarithmic order. And the problem you can see immediately. The problem with this is that once you have, or you always try and resum some log of like s over t, and you count in how many of those logs you do. But once you go crossing symmetry is like s to minus s, and what that does is related to I pi if I just take the log. And so those pieces, if I have a strict logarithmic counting, I've dropped that I pi because I say like an I pi is not a logarithm. And so that is where the failure, so you can just see manifestly that at any fixed logarithmic order, it will never obey unitarity. And so what one has to do is to, so in this, you can kind of draw, there's some kind of like space of, you can kind of organize these by the number of these like intermediate normal loops and the number of exchanges. So if I just draw without any intermediate things, the way that it works in the effective field theory is essentially this gives like a log from this loop. And if I just have one of these diagrams with no, this gives the I pi. And so this gives like the I pi squared, etc., etc. And so normal renormalization group flows you, so if I have like two loops, this is like log squared, and then like this. And so normally the problem is you resum in like columns. So this is like leading log or like one loop in the enormous dimension. This is like next to leading log. And then the problem is if I take this diagram and rotate it, it maps me to, for example, this. And so one way of doing this is that actually these are technically easier to calculate. And so we are able to, you can kind of trivially calculate higher loop Regge trajectories by relating them down to here. So that doesn't solve your problem, but it allows us to compute things. But somehow what you have to do is to like resum, or you need to reorganize in some like diagonal direction.
But in the case of Parmon, it's even worse, right?
Or the palm is still, it's related to this problem that you need, it's still related to this problem that you have, like the iPies and the palm you need this one as well. And so it's coming, this is kind of where the problem begins, is that you have a fundamental issue with how you organized it based on this logarithmic counting.
So, okay, so you have
so-
to do the diagonal, which
Yes.
is...
So right now one can resum in these columns, and one can also resum now this way, which is kind of like it's some form of, so these, because these are not, or keeping them as an iPi, what really happens when you sum up this is it's some e to the iPi, which is like 1. And so that's what restores unitarity. And, or at an amplitude level, that's what restores unitarity. And so you need to somehow do it in a way that respects that. And
is there anything conjecture known about the convergence?
no, yeah, no.
Likely to be asymptotic?
Yeah, almost certainly, yes. Yeah, that's the default, yes.
By the way, what is the status currently of the lower cross section experimentally?
So I am not the expert on that but I can, yeah. So there's these experiments, for example, the LHC, like Totem and stuff that have been measuring it. And there's also renewed interest in kind of BFKL for this electron-ion collider. And so people have been trying to come back to some of these old calculations. But as you said, or the problem in all those is that you need some hierarchy here, and then the problem is, for most physical things, there's not really much of a regime where this has occurred. So even in fits to this forward scattering data, one can ask if you ever even see, or like moderately forward scattering, if you ever even see indications of BFKL. And you essentially don't, because you're never in a regime where this is big enough. And so you can now just compute things to like 3 loops in perturbation theory, and that's sufficient for resumming these. And so experimentally, I think there's not much, this is yeah.
But still, it's fascinating to know how it really behaves.
Yes, yeah, and that's kind of related to this original, that non-perturbatively it better be okay.
Well, it's certainly better be consistent with the material.
Yes, yes, and that's from this, in this thing, what's happening is that you get this whole pile up, and even in perturbation theory, what's happening with these, so these need to somehow go below, and it's not understood at all what happens. And so one would like to better understand that. And trying to resum, or making it consistent with unitarity is very...
It looks like, experimentally, it looks like it saturates this rigorous bound.
Yes, yeah.
Although it can also be fit to something which violates the rigorous bound.
Yes.
Experimentally, it's hard to conclude, but
Yes.
assuming it saturates, that's a qualitative feature
Yes.
of the real world.
Absolutely,
which
yeah.
is not understood.
It is not understood at all, yeah.
Real challenge.
Even one would like, so let's say for that is to, even if one couldn't compute it, that you can draw like a schematic of what you hope to happen in this picture, and that, I think, it's not even understood as a like wish, or same as resumming these, how you would hope to...
Well, there's two things. Is it log S squared, which is the bound,
Yeah.
which is some qualitative feature of QCD,
Yes.
and then there's a number.
Yeah. And unfortunately, I think neither of those...
Pure number
Yeah.
which needs to be calculated.
Yes, and I think neither of those are... So for that, one is falling very short.
And the lattice doesn't help.
The lattice currently doesn't help because it's very deeply
Lorentzian.
Lorentzian.
And quantum computing, what is it? Quantum computing? That's a challenge.
So for real, that's very hard to make, or even to make it unitary in perturbation theory is not understood. And so that's a much smaller problem, which one has to first deal with. And so, yeah.
Do you reproduce Bolitsky-Kovchegov in any regime from your theory, or that's somehow different?
So this is one thing we're trying to fully understand, is Yeah, is one needs, because for us it's really, so any of these, so this, it gets like the standard BFKL, like the non-4 BFKL. But the BK, there's, yeah, it's, because it's kind of a, it's coming for us, we're kind of splitting it into these different pieces. And so there you need to.
For you, Wilson line is like close to identity, it's perturbative.
Exactly, yeah. Exactly, yeah. And same as like one should, from this, like from this whole hierarchy, be able to get these like BGM walk or any of them. But for us, it's really organized because we split it into these sums, and someone has to kind of combine these into some like function or some more complicated equation. But for us, it's really close to the identity.
Okay, let's thank Ian again.
What you showed, I mean, this diffusion, I mean, it looks